All right, so now we are going to talk about annuities due. Previously, we talked about ordinary annuities, but this is a different kind of annuity. So deposits in savings accounts, rent payments, and insurance premiums are typically examples of annuities due. Unlike an ordinary annuity, an annuity due has the periodic payment made at the beginning of the period. So that is the difference between the two. That's the important thing that you need to look at there. So example 5 says, suppose you invested $100 at the beginning of each year for 5 years in an account that paid interest at 10% compounded annually. How much money would you have in the account at the end of the 5 years? So I've gone ahead and drawn my timeline again. We did a very similar example when we started talking about ordinary annuities, but in that example, payments were made at the end of each year, and so our timeline looked like that. However, now that we are talking about annuities due, we are making payments at the beginning of each time period. And so if we thought about how much interest these things accumulated, now that we've started at the very beginning with that $100, that's going to have a chance to gain interest over 5 years. So our exponent for the 1.10 is going to be 5 there. And then here, that would be 100 times 1.10 to the 4th power, 100 times 1.10 to the 3rd power, and that pattern would continue. Okay, so that means that our future value of this annuity due is going to be the sum of these 5 terms. Now, again, it's going to come in handy that we know the sum of a geometric sequence. And let me very quickly remind you the formula for that. So if we're summing the first n terms, it's going to equal the first term times 1 minus the common ratio to the nth power all over 1 minus the common ratio. So I'm just going to put a plus sign between all of these. So we're adding up those 5 terms. So in this case, our future value, or the sum of those, would be the first term, which is 100 times 1.10. And then the rest of it would look very similar to what we were dealing with before. In the example with the ordinary annuity, we didn't have this 1.10 here, but now we do because that's what's in the first term of our sequence. And then we have 1 minus the common ratio, which is 1.10, to the nth power, which in this case is 5, over 1 minus 1.10. So really, the only difference between this example and that first example that we saw is this thing right here. So I'm going to go ahead and throw that into my calculator. So I went ahead and I threw that into my calculator, and at the end of the 5 years, we will have $671.56. Now, if you go back to that previous example, you will see that that's about $61 greater than the ordinary annuity, and that should make sense because what's happening is we're putting in money at the beginning, at the very, very beginning, and so that money has a little bit more time to gain interest. So that it should make sense in this scenario that we're getting slightly more money, about $61 more than the example where we were talking about the ordinary annuity. So I said in this example here, again, that the only difference between the two examples was this term here. And if we wrote that in general, that is 1 plus whatever the interest rate is. And so if you come down here to the future value of an annuity due, it looks exactly the same as the future value of an ordinary annuity, except we are now multiplying by 1 plus the interest rate. So keep that in mind as you are thinking about these problems. Now again, just as a quick refresher, if we are talking about annuities, there are two types of annuities. There are the ordinary annuities, and there are the annuities due. So the annuities due are the ones where the payments are at the beginning. And the ordinary annuities are where the payments are at the end of each time period. So think about that as you are working on problems. So example 6 says, find the future value of an investment if $150 is deposited at the beginning of each month for 9 years at the interest rate 7.2% that is compounded annually. All right, so the regular payments that we are making are $150. And the number of terms, we have each month for 9 years. So we would multiply 9 times 12, which is equal to 108. And our interest rate, we have an annual interest rate of 7.2. So if I converted that to a decimal, it would be 0.072. And we are compounding monthly, so I would divide that by 12, which gives us 0.006. And the future value is what we are solving for. So the notation we do, the notation that we use for that is S sub the word due, and that is what we are trying to figure out. Now, very importantly, we want to establish that this is an annuity due because we are making the payments at the beginning of each month. So that's how I will know to use this formula here versus the other one. Okay, so S sub due is equal to 150 times 1 plus 0.006 to the power of 108 minus 1 all over 0.006, and then we want to multiply that by 1 plus 0.006, which is 1.006. Okay, and if we throw that into our calculator, you should get that the future value is approximately $22,836.59. All right, let's move on to example 7. It says, suppose a company wants to have $450,000 after 2.5 years to modernize its production equipment. How much should be deposited at the beginning of the current quarter to reach this goal if the company's investment earns 6.8% compounded quarterly? Again, we want to notice that it says beginning of the current quarter. So we are talking about an annuity due. And in this scenario, we have the future value of the annuity due. It tells us that it's $450,000. what else do we have? So we have n, which is equal to, it's over the span of 2.5 years, and we are compounding quarterly, so that means that it's 4 times per year. So if we multiplied 2.5 times 4, we would get 10. And then our interest rate is 6.8%, written as a decimal, that is 0.068, and we are dividing that by 4, which gives us 0.017. Okay, so it's asking how much should be deposited at the beginning of the current quarter to reach this goal. So the R value, the regular payments at the beginning of each quarter, is the value that we do not have. So that's what we're solving for. So if we plug in the values into our formula, we have 450,000 equals R times 1 plus 0.017 to the 10th power minus 1 all over 0.017. Oh, I'm running out of room. So that is going to be multiplied by 1.017. Okay, and then we are going to solve that for R. All right, so I threw that into my calculator and we got that the regular payments at the beginning of each quarter should be approximately $40,967.39 if we want to reach the goal of having $450,000 after 2.5 years.